Hello everyone. Good night. Welcome to my YouTube channel. My name is Diandra and my student number is 5017-241-1069. So in today I'm going to review paper on GPR application. So the title of my paper is Combined Application of GPR and ERT for the Assessment of a Wall Structure at the Heptapyrgion Fortress. So which is basically it's on Greece. Yes, interesting, isn't it? So yeah, welcome. Just want to say welcome everyone to my YouTube channel, and therefore let's just continue to the next topic. So, okay, so for today's topic, what we're going to talk about is mostly about the background and objective, the problem, methodology, which is the method that is being used or the ways of it, and next is the result and the findings. Okay, so this this paper occurs on the Greece. So as you can see, this beautiful fortress. And what's wrong with this? What's the problem of this? And next, we're going to look on what are the problem. So yes. So next, the background. So this happened, as I said before, it's on Heptapyrgion, specifically Tower P3. So this monument is basically one of the uh, national treasure, as you can see, and the monument of Victorian Fortress Judicale is located in Thessaloniki in Greece. So this is a Byzantine in the era fortress, so built in multiple phases. So it's been here for a long time. And as I said before, this is a significant historical and cultural importance. And what actually happens to the tower? Why does it need some GPR application on this? Well, this specific tower, especially in P3, has suffered a damage in the 1978 earthquake, so it has been underwent grouting restoration in the 90s, and it's going to be restored again on the 2012. And here's the thing, what are the problem of this? So as you can see, this is the visible structural damage and the areas of high moisture at a various location of the hypogeneous Greece fortress. So therefore, since 2012, it has been conservated. There's noticed a persistent dampness on the first level of the tower north face. So the critical issue of this area is completely inaccessible from the inside. So as you can see, no one can see what's actually going on inside of the wall, and therefore, how do we go through look at it? How do like are the workers going to just broke the wall and then just check one by one, and it's not effective, right? So therefore this area is inaccessible from the interior, and it has an unknown long-term effectiveness of grouting and internal defects. So therefore the main objective of this is to non-destructively investigate the internal structure of the P3's wall to guide the future restoration. Yes, so I think it's clear enough for the problem, like what is it, what's the problem. So therefore, we move on to the aim of study. So we have five specific aims to achieve. So first one is to identify where is the high moisture content, where the area contain the most water inside of the fortress, and next is to detect the structural defects such as crack or void, and next is to map different construction phase of the wall. So therefore, this is a future restoration. And next is to cross-validate result using two geophysical methods. So we're going to use GPR and ERT, but in this case, we're going to focus more on the GPR. And five, we're going to use a numerical modeling. So this is one of like the open source GPR Max to improve the data interpretation. All right. So why did we use GPR? Well, it's pretty simple. Why did we use GPR? Well, simply because GPR has a high resolution, as you can see in this picture. Once you send out the transmitted waves, and then it will reflect it a wave back. So For this case, especially in a small cracks and or voids in a building, and it's more effective if we just use a GPR to send out, and it is actually very sensitive to the water, and wet zones will attenuate the radar signal. So also the GPR can see the layer structure like it's different construction phase. So I point out some of the point is where the sensitive to the moisture when it it will sense the signal is attenuates, and also it can see a layered structure of the construction phase. And this is the simple methodology. We're going to use the GPR, ERT, and GPR numerical modeling GPR Max software. So for these two, GPR and the ERT, it's taken in the same time. So it's basically just doing by itself, but at the same time. And next, for the setup. So this is the survey design. As you can see, the wall is constructed using the design acquisition, if I'm not mistaken. The GPR Max is being used in order to help draw the image, and therefore it has a 8 parallel horizontal line of the extreme wall. As you can see, this is the first line. Oops, first line. 1, 2, 3, 4, 5, 6, 7, 8, and this is how they're going to take using a GPR Mala, where this is a small one. This one, if I'm not mistaken, is the 250. Yes, and like that, and they're going to stick out and just walk through all the lines till the end. And at one line, at the height or it starts at a zero point 0.5 meter, and then at the top is 1.9 height, and the line space between these two is 200 centimeters, and each line length is a 9.2 meters. So from the start, from the end, so this is like each edges, there are zero point 0.4 for each edges, so there's aiming for all this long line. Okay, so next we're going to move on the setup again. So just use the same example image. So the primary antenna is 500 m MHz, where it's best to compromise between depth and resolution. And the second one, the secondary antenna, it's 250 MHz. So for a specific target on the lines like 4 and 6, it's for deeper penetration. And the key parameter of this is like the trace depth, it's used like 0.04 meters, and the velocity is around 0.11 ms. So it's for the calibrated on the wall, and this is mostly on the processing that we're going to talk later on. So this is the flowchart for the processing GPR, where it starts, and then we give the filter. Some of the filters like such as DWOW, time zero, background removal, wave number filter, deconvolution, bandpass gain, Hilbert transform, and till the end. And here's another thing for the GPR setup. So for the GPR Max, it actually helped us to build a realistic future wall model, such as brick, mortar, crack, and wet zone, especially in the fortress, gave us really good image. So it also assigned electromagnetic properties such as permittivity and conductivity. And third, it simulates a GPR survey on the model. And fourth, processes synthetic data exactly like the real data. And next, number 5, it's compared to validated interpretation. So I will give more later on, bigger picture. So here are the result of the data that has been taken. So first one, I'm just gonna show you example for the for the blue line, which is the most noticeable. This is the horizontal reflection, as you can see right here, and in this like red or and orange areas, it shows the diagonal refraction of the arrow. So this what we will look mostly at from this result. So yeah, red and orange indicates the possible cracks or voids, lateral air reflection, And blue line may interface between two subsequent wall construction phase. And next for the moisture mapping. So after the Hilbert transform, it will the moisture becomes very clear, such as like the blue-green colors mean the low signal amplitude, and the low signal to the high moisture. And the moisture on the left, on the eastern side of the wall, is the strongest. Is the strongest in the lowest line near the ground. So moisture is likely rising from the ground. So you can see, uh, this is like one of the result from line 1 until line 8. And moving on to the construction, so as you can see, it appears a strong horizontal reflection appears on every same line of depth, which is like on this height, which is around like 1.7 meters depth, appears on all eight, not just on the wet area. That means it's a real interface. So historical record says the tower was built in phases. So there's reflection uh, two two construction phases. So the GPR can tell us the history of the building indirectly. So yeah, as you can see, there are this line which actually it indicates on the same all in the same line on the same depth, which is like around between 1.5 and then 2 meters. So yeah, moving on. For the possible cracks and void, I use one of the example here, and this is from the GPR Max, just to give a better picture and understanding. So as you can see on the red arrow in line 2 and line 4, so I use, if I'm not mistaken, it's line 4. It shows like a possible crack on the red line, and also a wider of strong reflection on red rectangle right in here. Well, that and therefore, and then the modeling voids produce strong localized reflection regardless of the moisture. And yeah, so it shows that the void and cracks produce exactly this kind of strong and localized reflection. Therefore, these are likely the structural defects, cracks, or small void happening in here. And here I wanna short explanation about the ERT. So ERT was done to confirm the moisture of the GPR. So the ERT is like the complementary for the data, so which makes us more sure about the GPR result. So in just so yeah, so therefore ERT was done on the same grid time. So this is basically the same line between these two. This one is GPR and this one ERT. And also low resistivity equal to high moisture, which mean in the low area can contain like the blue zone in here contains, and also the blue zone which contains a water content. And also ERT shows moisture on the left side near the ground. As you can see, like in this, most of on the left part of each line indicates a low resistivity, and then low amplitude, which mean it indicates a moisture on the side. And also the cross validation confirmed GPR moisture interpretation. Yeah. So therefore it basically can help each other out for validating each of the data result. And next, this is for the modeling validates GPR interpretation. So this is for like to make more convincing. So after the survey built, so as you can see, the model 13, uh, this part that include the two construction phase, moisture zone, and crack area. And this is basically the show you between the real one and the simulated one. And it's like comparing the result to help like the constructor to have a better picture. And based on the modeling data, it's basically confirmed that the interpreted features are real. It's basically almost the same on what indicates. So this is like the GPR max, and this is the real data. It will like draw out this 3D image. And therefore, we're moving on to the main conclusion. So GPR has successfully identified the moisture distribution, which is on the eastern side, and the ground originated, which is below here, and also the construction phase of the boundary. It gives like the history of it. And next, numerical modeling GPR Max, a proof essential for validation, which is the the 3D one. And next, the GPR and minor ERT check is reliable for non-destructive assessment. Oops. And okay, so after the main conclusion, there's some a second thoughts, or basically what the paper have taught me. So first, I'm just gonna read out the multiple method in geophysical investigation is highly valuable for heritage monument assessment. So like for example, in this case where it helps to reconstruct the fortress without actually destroying it. So this helps for like a for example in the future, such as the Great Wall of China, if they are going some under construction, it can we can apply GPR method for this case. And next, no single geophysical method is universally ideal, so each has strengths and weaknesses. And like in this case, the GPR is not reliable by itself, but therefore it needs a two method for validates each other. And next, the GPR strength is high spatial resolution and can detect localized structural defects. And the GPR limitation is the amplitude response is difficult to convert into a physical qualities without calibration. And next, for the method, the the ERT strength provides a quantitative measure of bulk electrical resistivity, which correlates more directly with moisture content. And for the ERT limitation, it inherently lowers spatial resolution compared to GPR. So combining methods on the same grid under analytical on condition allows exploitation of complementary strength. The combined approach achieves level of confidence that neither method could attain individually. So yeah, basically same as this one. It helps validates each other. And last second, numerical forward modeling should be a systematic integral component of the workflow, not merely an afterthought. And last, this integrated workflow exemplifies best practice that should be adopted more widely in applied GPR investigation. And this is the paper that I got from, which is the thanks to Dimitrios Angelis, Patrodios Trusolos Groskastoskas, George Vargamizis, and some Greece name. Thank you so much for the Department of Geophysics, School of Geology, Aristotle University of Thessaloniki. So that's all for my presentation. Thank you for listening, sir.